Hello, Physics 20. Today we're going to be starting Unit B, or Unit C, and this is our circular motion unit. We're also going to look at work and energy in the second chapter. So we're going to start Chapter 5, which is all about circular motion. And just remember, circular motion is motion in a circular pathway. So if you think about a roller coaster and you go through a loop, that would be circular motion. Or if you think about a, what would be another thing? You could think about a Ferris wheel going around, even a wheel turning, that would all be circular motion. You could also think about the Earth orbiting the sun, that's also circular motion. Okay, we're going to be paying attention or looking at uniform circular motion. So this is just that motion, that circular motion that's in a circular pathway, and we are going to be moving at a constant speed. So our speed is not going to be changing. So what we would say, the rotational, i.e., the rotational speed is constant. Okay, so if we have an object that is rotating tangentially in a pathway, if we were to release it, it would travel along a straight pathway. So it would be launched in a straight line. So we call that that it would want to move off tangentially. So just like we drew those tangents on those curved lines, same idea, our object is going to want to fly off in a straight line at the moment that we release it. Okay, so I'm going to show you this video here.
Imagine you've got a tennis ball attached to a piece of string, and you start swinging it in circles. Whoa now, watch out for your buddy. Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird-sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast on a roller coaster, you can thank the centripetal force.
Okay, so let's write that stuff down. So what does this mean? If we had an object on the edge of this tire and the tire was rotating around, so think of like if you had a rock stuck in the wheel, the object is a radius distance away from the circle. So this is the radius of the circle. When we cut that string, or when it's released from the wheel, it is going to fly off in a straight line. So that would be our velocity. Now, it's going to move at a perpendicular direction to the radius. The speed, right, is a scalar quantity. And we remember that it only has magnitude. So speed is a scalar quantity, has magnitude. And in this case, the speed is constant. So the magnitude is not changing. What is changing is the direction. So we have velocity, which is a vector quantity. And the the velocity has direction, or has a magnitude, which is going to stay constant. So you can think of the magnitude of that speed, or the speed magnitude is going to be the velocity magnitude, and it's going to stay constant. The thing that is changing, that is going to give us that acceleration, is the direction. So this velocity has magnitude and direction, and it's the direction that's changing that is going to give us the acceleration. So as the wheel turns, the speed is constant, so the magnitude, but the direction changes. Therefore, because that direction is changing, we can say the wheel is accelerating. So if we wanted to look at the change in velocity over time, we could pick 2 points on our wheel. So I could stick with my first point, and I could call that A, and this would now be the velocity of A. I could pick a second point along the wheel, and I could call this point B, and then my tangential velocity would be flying in this direction, or moving in that direction. Sorry, that should be a B. The magnitude of those two velocities are the same, but now the direction is different. So if I want to solve for my delta V, I'm going to subtract A from B. Well, usually when we're doing resultants, we want to add them up, but now we're doing subtraction. So what we're going to do is we're going to take our vector A, which is pointing in this direction, and we're now going to draw it in the reverse. So it's going to point back in this direction. So we've just reversed it. So now we are subtracting B from A, but again, it's a sum. And so now the resultant here will be the change in velocity. And what you'll notice is that the change in velocity when the A and B are far apart is not quite pointing to center. But if I was to make these two distances closer and closer to each other, this change in velocity would then start to point towards the center. Okay, so that's where my change in velocity is really pointing, towards the center of the wheel. So acceleration is when there is a change in velocity. Because the change in velocity is pointing to the center, our acceleration is therefore going to point towards the center. Okay, we call that centripetal acceleration. So acceleration that points to the center is called centripetal, and that just means center seeking. So centripetal acceleration. And when you look on your data sheet, you will see that we now have centripetal acceleration equations. So the symbol for that is an A and a subscript C. So if we have a net force now that's not zero, because now we have an acceleration. If we have acceleration, therefore acceleration is not zero, that means we have a non-zero net force. And we are now going to call that centripetal force. And we write this as F with a subscript C. So this centripetal force is the force that is keeping the object from rotating around the center point. It is pulling the object to the center. The object wants to fly off tangentially, but the force is keeping it to the center. So this centripetal force is really what we call a net force, because it can be a variety of forces. Okay, so it's all the forces that are center seeking. They want to keep the object moving to the center. So we're going to pause the video here, and we're going to do a demonstration with a water on a tray, and we're going to rotate it around, and we're going to see what happens. Okay, now that we're back, Why does the water not fall out of the glass? What is it experiencing as it's moving in that circular pathway? So, the water is moving in a circular pathway. And it wants to fly off tangentially. So it wants to fly off, but it doesn't. And wants to move off tangentially. It doesn't move off because there is a centripetal force. So it wants to move off tangentially. The centripetal force, Fc, pulls the water in the cup that the water's in towards the center of the pathway. And in this case, that centripetal force is the force that's in the string. And so it's a tension force that's keeping it from flying off. Okay? And it pulls it towards the center, therefore the water keeps moving in a circular pathway. And that's an example of centripetal force. So some misconceptions before we get moving here. A lot of times when you're on those roller coaster rides, you feel like as though you're trying to, like the force is pulling you out of the car or that you're trying to fly out of the circle. But really, that centripetal force is acting to the center. So centripetal force and centripetal acceleration is always towards the center. So centripetal force and centripetal acceleration are always towards the center. So they always point to the center. They never point out of the center or away from the center. Okay? Fc is like a net force, so it can be any force. So it can be any center-seeking force. So, for example, we had tension in the string attached to the platform that was holding the cup of water. We could also have gravity, which is keeping the Earth orbiting right now around the sun. We could also have a normal force of the roller coaster pushing, the roller coaster rails pushing on the car towards the center. Okay? We could have the force of friction that's keeping the car from sliding off the road on an icy or wintry day. So there are lots of different forces. As long as they're moving to the center, it can be considered a centripetal force. And the centripetal force is a net force. So it can be the sum of a lot of different things. So F net is like F net. But we just say centripetal force because we're talking about circular motion. So if you would like, on page 247, there are some check and reflect questions. If you wanted to go through it, that would be kind of a good way to review. But we're going to stop the video here, and we are going to continue on with 5.2 in the next video.